Hello and welcome. This recording is session 8 of an 8-part series on the topic, Moving Towards Improved Earthquake Performance and Resilience for New Buildings. My name is John Sherstobitoff. I'm a structural engineer focusing on earthquake engineering for buildings. This series of recordings is part of the MBAR initiative by BC Housing. MBAR includes and promotes the consideration of resilience for new buildings for natural disasters such as earthquakes. The list of 8 sessions is noted on this slide for your future reference. Today's session is on earthquake instrumentation. So earthquake instrumentation, a consideration for new buildings. There's typically 2 types of sensors that are readily available today: earthquake early warning and strong motion instrumentation. Earthquake early warning can detect the earthquake and provide a warning beforehand, maybe a few seconds to maybe 90 seconds in the Vancouver area. And the photos on the right show a typical alarm and strobe in an office building and the sensor that's located in the basement. Strong motion instrumentation can provide near real-time information after the earthquake about the specific building of that specific, building for that specific earthquake. The sensors can be located above the ceilings, hidden, and the control center can be easily adapted into an instrumentation room or electrical room in the basement. So how does the earthquake early warning work? When a rupture occurs, the shaking arrives at the site in several ways. The P waves, which travel faster, arrive first. They're small, they're undetectable by people, but detectable by instruments. The damaging shear waves arrive next, again at a little bit later time. And the difference in arrival time becomes the warning time. And you can see approximately 1 second of warning for every 8 kilometers that a building is from the hypocenter of the earthquake. The illustration on the right shows that for the Loma Prieta earthquake in San Francisco, had that system been in place, there would have been some 10 seconds of warning before the strong shaking occurred. BC, that warning time varies from 1 second to 90 seconds depending on the distance. Again, in BC, we can have very shallow crustal earthquakes almost directly below a building, and maybe only 1 second of warning is possible. If the subduction earthquakes, which is offshore, starts perhaps further south of BC, there can be up to 90 seconds of warning. And there's 2 different types of systems: a fully on-site system where the sensor detects the P wave and sets off the alarms for that building. But again, that waits for that P wave to get to that particular building. A network utilizes all the earthquake early warning sensors throughout BC, which can give even more warning. For example, a sensor on Vancouver Island could detect a subduction earthquake and alert a building in Vancouver much earlier than waiting for that P wave to arrive in the Vancouver area. Early warning systems are currently in operation in quite a number of countries around the world, as illustrated by this map. The National Resources of Canada, NRCan, is currently developing a national earthquake early warning system, with intended to be fully online in 2024. The first installation was in BC at Horseshoe Bay in March 2022. And again, there's a link there that really explains their system and their vision for this national system. Earthquake early warning can trigger automatic actions within a building or infrastructure, such as triggering trains to slow down or stop, stopping traffic going onto bridges or into tunnels, diverting air traffic, opening fire hall doors or ambulance doors, and moving elevators to the nearest floor and opening the doors, all done automatically. And the illustration at the right is just some various times for various actions that allow some advance warning. Again, George Massey Tunnel in the Greater Vancouver area has had earthquake early warning since 2009. And again, to be able to stop people from entering the tunnel when such a warning goes. Private schools, the Roman Catholic Archdiocese of Vancouver, have had sensors installed on a number of sites and enabled to alarm some 30 buildings should strong shaking be expected. Public schools, there's a number of public schools as part of the seismic retrofit program that have both earthquake early warning and strong motion instrumentation installed. Again, and this has been done on a district by district basis. Ocean Networks Canada also has installed quite a large array of sensors in BC. In 2016, they got further funding from Emergency Management BC, and they installed 44 additional earthquake early warning sensors by 2019. And there's an excellent report here noted to read about that system. The Canada line in Vancouver is currently connected to that system with regular testing of this earthquake early warning, and they have automatic provisions to either slow down or stop the trains. Moving on to strong motion instrumentation. Natural Resources Canada has quite a number of sensors in BC. And again, these are typically to understand the acceleration and the velocity and displacement and intensity of the earthquake. That information then can be rapidly sent out to the community to understand where the strongest shaking occurred and if your building was in that or near that area. Ministry of Transportation and Infrastructure has a system, BC SIMS. They collect data from instruments on their bridges and other infrastructure, and they can produce what are called shake maps. And you'll see on the right an illustration of Haida Gwaii, the large red dot being the epicenter, and again, then the colors showing the intensity of the strong shaking to automatically alert people in BC of where the earthquake occurred and the level of intensity and how, nearby to that epicenter. Is your building in that area? Finally, an illustration of a building in Vancouver that's fully instrumented and operating today, both for earthquake early warning, which has a sensor at the very bottom of the basement, and then earthquake early warning system alarms and strobes in the upper 4 floors, again, to alert the occupants of a impending earthquake. Similarly, strong motion instrumentation to fully understand how that building behaved relative to its original design. Again, another photo of those strobes and alarms on the floors, and that modest sensor bolted to the wall in the basement. And the strong motion instrumentation, again, the similar photos to earlier. And again, the beauty of this is that it's specific for this building, for the earthquake that hits at that given time, and it really does help assess the damage state of the building to augment just visual inspections that are normally done. And it really does enable a more confident decision to enable occupants to remain safely in the building. So the kind of things that these instruments pick up is they can measure the deformations of the building, the total deformation, the interstory deformation between floors, the peak one during transient shaking, any permanent residual drift of the building, floor rotations, accelerations, and again, that the design response spectrum it can plot out that we talked about in previous sessions, all to compare to the original design. Did the building experience something less than the original design, more than the original design, or about what it was originally designed for, with the ability to give readouts, say green, that say it should be very safe because it's well below the design level, or red, where it's much higher than design level and really should evacuate the occupants, or yellow, where it's about the design level and perhaps some further investigation is required. The cost for that particular building was about $80,000 for installation, including training. And again, but the number and type of sensors can be tailored to each building to go from a very small dollar value to obviously more significant for much larger buildings and more sensors. What should be allowed is an annual maintenance budget, again, just to make sure that the sensors are working and to allow for repair or replacement should any sensors or the system go offline. And it's variable based on the vendor used, the owner's system, the philosophy, and the number of training earthquake early warning simulations each year. So in summary, earthquake early warning is moving towards a national system by 2024. In BC, it can provide warning that strong shaking is coming from between 1 and 90 seconds. and can also be set up to provide a variety of automatic options, or simply to warn building occupants that a strong shaking is coming, giving them more time to drop cover and hold on. Strong motion instrumentation. Again, it's already been installed in a variety of BC's infrastructure and in various buildings. It can be used to provide shake maps to understand where the strong shaking is. And again, for a specific building, really enhance decision-making to hopefully enable occupants to remain safely in the building or make a confident decision that they actually do need to evacuate. There are many, many vendors providing these sensors and the software. And again, there's a real hope that there'll be standardization within BC as we move towards a national system. So that concludes this session and this session regarding performance and resilience for buildings. If you would like more information on this topic, please contact me at the email address noted below. For more information on MBAR, there's an email and web page address noted. Thank you for attending this session, and I hope you join me again for more sessions in this series.